The next class of reactions we want to talk about are the nucleophilic acyl substitution reactions. Up until now, we've used nucleophiles to add to the carbonyl to generate a tetrahedral intermediate in a process that's reversible if the nucleophile is a good leaving group. Furthermore, the carbonyls that we've used are aldehydes and ketones, which have a rather low-lying pi star CO orbital. Right, so the non-bonding pair of electrons on the nucleophile attacks the pi star CO, forms this tetrahedral intermediate that then gets trapped by a proton to give you a variety of products, such as the acetal, the cyanohydrin, and the gem diol. So what would happen if we now had electrophilic carbonyls which were not aldehydes and ketones? Right? Would they have the same reactivity or different reactivity? Right, so let's take a look at the following reaction. Let's say we have some carbonyl that has a leaving group on it, right? Some X group. And let's say we want to determine what would happen if we were to react this with a nucleophile. Well, what would happen is that you will get a reaction known as a nucleophilic acyl substitution reaction. Right, so the pi star CO is still going to be our LUMO. And so what you can get is, and this may or may not be reversible, you can get a nucleophile to attack the pi star CO, forming a tetrahedral intermediate. Right, so the non-bonding pair of electrons on the nucleophile is our HOMO. So the new tetrahedral intermediate will look like this. We have a new carbon nucleophile bond, and then we have an X group. Now this tetrahedral intermediate is quite unstable. In the past, where we've protonated off the oxyanion, what is instead going to happen is we're going to regenerate the pi bond. Right, so the non-bonding pair of electrons on oxygen come down to form a new CO double bond, and then X minus is going to leave as the leaving group. And so again, we've got this system here where we could be reversible, and X minus is the leaving group. So this mechanism is known as the nucleophilic acyl substitution mechanism. Right, like nucleophilic addition mechanisms, the nucleophile attacks the pi star orbital, resulting in this tetrahedral intermediate. However, the intermediate can collapse with loss of the leaving group. Right, and this can occur under both basic conditions and acidic conditions. Right, so let's draw out what would happen for basic conditions and acidic conditions. Okay, so under basic conditions, what's going to happen is we're going to have a carbonyl, and then we're going to have a deprotonated nucleophile as our nucleophile. So maybe let's have a nucleophile in the presence of some base. This is under basic conditions. What can happen is the base can deprotonate the nucleophile, make it nuc minus, plus obviously the conjugate acid. This nuc minus can then undergo nucleophilic acyl substitution. So nucleophilic attack onto that pi star CO. This happens because the HOMO has been raised by the deprotonation. Last step, finding collapse of the tetrahedral intermediate with loss of a good leaving group. And then you'll get the new carbonyl, which now has nucleophiles substituted. If we were to look at this from a reaction coordinate diagram, we would have the original carbonyl sitting here. The tetrahedral intermediate would look like this. And depending on what your leaving group is, it may or may not be the rate determining step. Right, so either step could be rate determining here. and this will depend on the specific nucleophile. Now, what if we were under acidic conditions? Well, acidic conditions is very similar, except now we're going to have a proton source is going to activate the carbonyl. Right, so instead of having a deprotonated nucleophile, what we're now going to have is a neutral nucleophile, but now we're going to have acidic conditions. And so what happens here is that we're lowering the LUMO. Right, so the carbonyl is going to become protonated, and now we have a really activated carbonyl. This lowers the LUMO, while this raises the HOMO. Deprotonation, this one lowers the LUMO. And it lowers the LUMO so much that the nucleophile, which is neutral, can undergo nucleophilic attack. And so when that happens, we get a new carbon nucleophile bond. But that nucleophile is still going to be protonated. We can get that deprotonating to form a neutral species. We get collapse of the tetrahedral intermediate with loss of the leaving group to give us a protonated substituted carbonyl, and then finally loss of that proton to regenerate the neutral, now substituted carbonyl. Okay. Types of nucleophiles that we'll be using for these nucleophilic acyl substitution reactions are really the same ones that we did for nucleophilic additions. Right, so those are going to be things like water, hydroxide, alcohols or alkoxides. We could have amines as nucleophiles. We could have something hard like LAH. Or a Grignard reagent, or an organolithium reagent, or a hydride reagent. Right, so all of the same types of nucleophiles that we had for nucleophilic additions will also be present in the case of nucleophilic acyl substitutions. There are, of course, others, though. There are more types of nucleophiles that don't fit into these categories, and we'll talk about those as we go throughout this section. Now, there are also various types of electrophiles that we might have. Right, so just like there's a diversity of nucleophiles, there's a diversity of electrophiles that can be used in this reaction. And we say that there's a reactivity series associated with these based on increasing order of electrophilicity. And so the reactivity series goes as follows. And so the first one is the carboxylate. Right, so this is a deprotonated carboxylic acid. This is the least reactive or the least electrophilic. Stepping up from there, we have the amide. And these R primes R and R double prime don't have to be the same. But this is the amide. Stepping up from there is going to be the ester. And the ester is about the same as the carboxylic acid. And then we have the anhydride. And again, again, R and R prime don't have to be the same. So this is called an acid anhydride. And then finally we have something known as the acid chloride. So the acid chloride is going to be the most reactive, or the most electrophilic. So there are several factors that control the reactivity of these carbonyl compounds, and in each case, what we're really concerned about is the energy level of the LUMO, the pi star CO. So we want to think about how that is impacted. If we lower the LUMO, the reactivity towards nucleophilic attack increases. Right? So getting to the tetrahedral intermediate requires really, really good electrophilicity. So that carbonyl carbon in each of these cases should not have a lot of electron density on it. And so in order to determine how much electron density is on those carbonyl carbons, we need to consider three factors: resonance, sigma donation, four factors: resonance, sigma donation, inductive effects, and electronegativity. So let's go through these one by one and try to think about why these particular electrophiles are more or less reactive than the others. Let's take the carboxylates and the amides first. Okay, so for carboxylates and amides, what we have here are lone pairs on either an oxygen atom or a nitrogen atom. And so if we're thinking about the electron density on the carbonyls, what we can do here is we can draw a resonance form which increases the electron density on those carbonyl carbons. Right? You're pushing electron density towards the carbonyl carbon right there. Okay, so in the case of the nitrogen, we push electron density, and now we have this species. Now we have to compare these two species. So why is it that amides are a little bit more reactive than carboxylates? Well, in both cases, we're making the LUMO higher. We're pushing electron density towards a region which we don't want to have electron density if we're trying to get attacked by a nucleophile, right? So this decreases the reactivity. In the case of the carboxylate, we've got negative charge on electronegative atoms, both of which are oxygen. But in the case of the amide, the electronegative oxygen atom bears a negative charge, but there's also a positive charge on the nitrogen. And so this isn't quite as good as the carboxylate. And so what it means is that your nitrogen lone pairs are they want to be sitting on nitrogen a little bit more than they want to be sitting on oxygen. They're not as willing to give up those electrons. And so if they're not as willing to give up those electrons, then there, of course, is going to be less electron density on the carbonyl carbon, because they're not going to undergo resonance delocalization. Right, let's take that same analogy and try to figure out why the esters and the carboxylic acids are a little bit more reactive than carboxylates and amides. So in esters and carboxylic acids, we have a situation in which we've got lone pairs on oxygen, and they can undergo resonance delocalization. But do they really want to undergo resonance delocalization? Well, if they did, we would get a system that looks like this, in which we've got one oxygen atom is negatively charged, but another oxygen atom is positively charged. And we know that electronegative atoms don't like to be positively charged. And so what this resonance form is telling us is that it doesn't want to be like this. It would rather be like this, in which the oxygen lone pairs are sitting on oxygen, not participating in resonance. And so if they're not participating in resonance, the electron density at that carbonyl stays a little bit lower. And so if it stays a little bit lower, it's more electrophilic, it's more delta plus. All right, let's think about the anhydrides next. So with the anhydrides, we have two carbonyls. And these two carbonyls can pull electron density away from the oxygen lone pairs. And so we have one set of carbonyls that are pushing the electrons this way. And we have another set of, or another carbonyl that's pushing the electrons this way. Okay? And so we have lone pairs on the oxygen that can delocalize via resonance, but because no single carbonyl is receiving all of this electron density, the carbonyl itself becomes more electrophilic. So each one of these carbons is more electrophilic. In other words, the lone pairs on oxygen are being pulled in both directions, which is different than esters and carboxylic acids, in which there's only one direction that it can go. So if we say that this is going to undergo resonance, we can show a resonance form like this. Again, not very good, right, because we've got positive charge on oxygen, but we've also got a resonance form that looks like this. Also not very good, because of the positive charge on oxygen. So the lone pairs on oxygen only contribute half as much electron density to each carbonyl. If half of the electron density is going to the left, half of it is going to the right. And that leaves the carbonyl carbons with less electron density, and therefore they're more electrophilic. The last one is the acid chlorides. So why is this one the most electrophilic? Well, this is the most electrophilic because it suffers from what's known as orbital mismatch. And so we can, of course, draw the lone pairs on chlorine delocalizing into the carbonyl to give us this resonance form in which we've got a positive charge on chlorine. And this is of course not good because you've got positive charge on a halogen, on an electronegative atom. But this resonance doesn't form in the first place. And the reason it doesn't form in the first place is because of orbital mismatch. So what do I mean by orbital mismatch? Well, let's look at this from a molecular orbital perspective. If we've got a carbonyl that looks like this, and we've got a chlorine atom right here and some R group right here. Okay, we've got a pi CC that's looking like this, and we've got a pi CO that looks like that, a pi star CO that looks like this. And in order to get resonance, we have to overlap the atomic p orbital on chlorine. And what you'll notice here is I've drawn a really, really big atomic p orbital for chlorine. Now, chlorine has lone pairs that are capable of delocalizing towards the carbonyl carbon, but because chlorine is in the second row, it is bigger and has poorer overlap with the carbonyl carbon. Okay, it has less resonance with the pi system. And so as a result, the lone pairs on the chlorine are contributing less. They're making the LUMO extremely low, right? Less electron density comes from no resonance occurring, right? And so the overlap that occurs is only really narrow right down in the region of that atomic p orbital that doesn't have good orbital overlap. Right? So the resonance delocalization doesn't occur as much, and you have a much more electrophilic species. Okay, so we've talked about why the reactivity is the way it is. Now what we want to try to do is to take each of these electrophiles and treat them with a generic nucleophile under basic conditions. So let's draw out the reactivity series first. So we've got carboxylate, amide, ester, about the same as the carboxylic acid. Then we have the acid anhydride, and then the acid chloride. And let's say we're going to react each of these with some generic nucleophile. Okay? Okay, so in each case we get nucleophilic attack onto the carbonyl carbon to form a tetrahedral intermediate. All right, so you should see the pattern here is that we're attacking the carbonyl carbon in the first step of a nucleophilic acyl substitution mechanism. It doesn't matter what electrophile you have, doesn't matter what nucleophile you have, you're forming a tetrahedral intermediate. Now what do those tetrahedral intermediates look like? First one looks like that. Second one looks like that. Ester looks like that. Carboxylic acid looks like that. Anhydride looks like that. And the acid chloride looks like that. Now also recognize that we could have performed this reaction under acidic conditions. The first step would be protonation followed by nucleophilic attack. Here we're choosing just basic conditions as the proof of principle. Now the next stage of the reaction is loss of the leaving group. So let's lose the leaving group in each case. Okay, so what would the leaving group be here? If we lost this leaving group, we would have regeneration of the carbonyl. So let me just draw that out in each of these cases. But in the first case, the leaving group that we'd get is O2 minus. And we've never come across an O2 minus leaving group, so this reaction doesn't work. Okay. This O2 minus, this oxide, is a very unstable species, and so it's not going to form as a leaving group. In the case of the amide, we can get collapse of the tetrahedral intermediate with loss of this leaving group. An amide anion. And this reaction really doesn't occur either. But I'll draw a sort of a dotted line to indicate that it will only occur under strongly acidic or strongly basic conditions. So I'll say only forcing conditions will this occur. All right, in the case of the ester, we can get collapse of this intermediate with loss of an alkoxide, and this does work, and what we get is the alkoxide anion. In the case of the carboxylic acid, we get loss of OH. In the case of the anhydride, we get loss of an acetate, or a carboxy anion. And in the case of the acid chloride, we get loss of chloroanion. Okay, so the ones on the right, the ester, the carboxylic acid, the anhydride, and the acid chloride are all viable reactions. And why are they viable? Well, there's a correlation with the pKa-H. So the pKa-H of those leaving groups, obviously for the O2 minus, the oxide, we don't have a pKa-H for that one. The pKa-H for the amide anion is about 42. For the alkoxide, the pKa-H is between 15 and 18. The pKa-H of hydroxide, in other words, the pKa of water, is 15.7. The pKa of a carboxylic acid, or the pKa-H of this carboxylate, is between 4 and 5. And the pKa-H of chloride anion, or the pKa-H of HCl, is -7. And so what this tells you is something about the effect of leaving group ability on the viability of these reactions. What you might notice about the reactivity series is that electrophilicity also correlates with leaving group ability. Right? So for reactions to occur via nucleophilic acyl substitution, right, leaving groups pKa-H must be less than 20 for the reaction to occur. Right, so the ester, the carboxylic acid, the anhydride, and the acid chloride all fit this category. Okay, so we should be able to take each of our nucleophiles and make any of the carboxylic acid derivatives that we have in the series, right? Some nucleophiles will be reactive enough or have a high enough HOMO to react with all the carbonyls, while others will only react with a few. And this is a process known as chemoselectivity. Likewise, many electrophiles will react with all of the nucleophiles, while others only a few. So what we can say here is, by choosing the appropriate nucleophile, you should be able to react one of the carboxylic acid derivatives on the right side of the reactivity series to make a carboxylic acid derivative farther to the left of the reactivity series, but not vice versa, not in the reverse direction. Okay. Now there are some exceptions, but we could do this either under basic conditions or acidic conditions. So let's start with the acid chloride. Okay, let's say we have this reactivity series. Again, it's carboxylate, amide, ester, about the same as carboxylic acid, anhydride, and then acid chloride. So let's start here. Could we take the acid chloride and make everything to the left of it? Okay. Well, we could take the acid chloride and react it with a carboxylic acid in the presence of a base. That would give us the anhydride, or we could react it under acidic conditions with just the carboxylic acid. And I'll put H plus there as a catalyst. So that's how you would make those anhydrides using either basic or acidic conditions. Now, how about making the carboxylic acid? How would we do that from the acid chloride? We would use water and some acid source. Now, why can't we use hydroxide? The reason why we can't use hydroxide is as soon as hydroxide comes into contact with the carboxylic acid, it's immediately going to give the carboxylate. And reality is any base will deprotonate the carboxylic acid to give you the carboxylate. Right, so formation of carboxylic acids must occur under acidic conditions, otherwise the carboxylate will form. All right, how about the ester? For the ester from the acid chloride, we can choose the alcohol, or we can have the alkoxide. And for this one, acidic conditions are not needed for ester formation. The alcohol is actually nucleophilic enough to just do it on its own. How about the amide? For the amide, you're just going to choose an amine. And notice that you don't need a proton here, because if you had a proton, it would just protonate the amine, and then you're left with a species that is no longer nucleophilic. And now if you wanted to take the carboxylic acid, the acid chloride and react it with hydroxide, you could get, of course, the carboxylate. All right, let's start from the acid anhydride. Right, so let's draw out the reactivity series again. This time we're going to start with the anhydride, and we're going to make the carboxylic acid. How do we do that? We're going to take an acid source and water. Again, you can't take hydroxide because that'll just give you the carboxylate. In order to make the ester, again, it's going to be the same conditions. We could have the alcohol, or we could take the alkoxide. For the formation of the amide, again, we're going to just take the amine, and then for the carboxylate, we're going to take hydroxide. Okay, so same reagents that we had for starting with the acid chloride. All right, so how about the carboxylic acid? How about if we start there? So again, let's draw our reactivity series. We should get into the habit of drawing this. You notice that I never took the acid anhydride and made the acid chloride from it, right? So we're only going from right to left in this series. All right, so if we start here with the carboxylic acid, how do we make the ester? We make the ester by using a proton source and an alcohol. This particular reaction is known as a Fischer esterification. Turns out that we cannot make the amide from the carboxylic acid, and the reason for this is that if you were to take the amine that you would need to form the amide, and in the presence of the carboxylic acid, all you'll do is protonate the amine to give you an ammonium ion, plus generate the carboxylate. Right, so this won't lead to any product formation. You can form the carboxylate though, right? Any base, of course, will give you the carboxylate. So all you're doing here is really a deprotonation. Okay, let's keep going. And so we've got the reactivity series once more. We need to now start with the ester. Okay, so if we start here with the ester, we actually can hydrolyze the ester to the carboxylic acid. And this is one of those rare exceptions where you can form something to the right of the reactivity series from something on the left. And really this is not really a rightward motion, right, because the carboxylic acid and the ester are about the same. But the reagents you would need for this are a proton source and water. How about if we wanted to try to form the amide? Okay, we would need an amine and some catalyst to perform this reaction. Or we can do this reaction with just ammonia as the nucleophile. And that would give a primary amide as your product. If you have R groups on those amines, that nitrogen, then you need a catalyst in order for this to work. And of course, you can take the ester and form the carboxylate by treating it with hydroxide. And finally, let's take a look at the last case, where we're starting with the amide. All right, so start here with the amide. As I mentioned in a couple slides ago, we can actually take the amide and we can make the carboxylic acid from it under forcing conditions. And that requires really strong acid and water in the presence of high temperatures. We can also take that amide and under forcing basic conditions, high temperatures, with hydroxide, we can also form the carboxylic acid. the carboxylate, excuse me. But then we can take that carboxylate and form the carboxylic acid by just protonating it with a strong acid. And so what you'll notice from this exercise is that only the acid chloride cannot be made from anything else in the reactivity series. And that's not entirely true, but that's true enough for now, and so you just have to stay tuned for how to make acid chlorides for a little bit later in the semester.